A marshmallow is a sugar-based confection that, in its modern form, typically consists of sugar, water and gelatin, which is whipped to a spongy consistency, molded into small cylindrical pieces, and coated with corn starch. Some marshmallow recipes call for eggs. This confection is the modern version of a medicinal confection made from Althaea officinalis. The marshmallow plant. History. The word marshmallow stems from the mallow plant, Althaea officinalis, that is a genus of an herb native to parts of Europe, North Africa, and Asia. The word marsh is used because the mallow plant grows in marshes and other damp areas. The plant itself has a fleshy stem, leaves, and a flower with 5 white petals. There is no exact date as to when marshmallows were invented, but their history goes back as early as 2000 BC. Ancient Egyptians were said to be the first to make marshmallows, and it was considered a privilege to be able to partake in its consumption. It was strictly reserved for gods and royalty, who took the root of the plant and used it as a medicinal to soothe coughs and sore throats, and heal wounds. The first marshmallows were prepared by boiling pieces of root pulp with sugar until it thickened. Once thickened, the mixture was strained, cooled, and then used as intended, whether it was being used for candy or medicine. The manufacturing process was limited to a small scale. In the early to mid-1800s, the marshmallow had made its way to France, where confectioners augmented the plant's traditional medicinal value with indulgent ingredients utilized by the Egyptians. Owners of small candy stores would whip the sap from the mallow root into a fluffy candy mold. This candy was called pâté de guimauve. It was a spongy soft dessert made from whipping dried marshmallow roots with sugar, water, and egg whites. It was sold in bar form as a lozenge. Drying and preparing of the marshmallow took 1 to 2 days before the final product could be produced. In the late 1800s, candy makers started looking for a new process, and discovered the starch mogul system, in which trays of modified corn starch had a mold firmly pushed down in them to create cavities within the starch. The cavities were then filled with the whipped marshmallow sap mixture, and allowed to cool or harden. At the same time, candy makers began to replace the mallow root with gelatin, which created a stable form of marshmallow. By the early 1900s, thanks to the starch mogul system, marshmallows were introduced to the United States and available for mass consumption. They were sold in tins as penny candy, and were soon used in a variety of food recipes like banana fluff, lime mallow sponge, and tutti frutti. In 1948, Alex Daumack patented the extrusion process, which involved running marshmallow ingredients through tubes. The tubes created a long rope of marshmallow mixture, and were then set out to cool. The ingredients are then cut into equal pieces and packaged. Modern marshmallow manufacturing is highly automated, and has been since the early 1950s, when the extrusion process was first developed. Numerous improvements and advancements allow for production of thousands of pounds of marshmallow a day. Today, the marshmallow typically consists of 4 components. These are sugar, water, air, and a whipping agent, usually a protein. The type of sugar and whipping agent varies depending on desired characteristics. Each ingredient plays a specific role in the final product. Development of modern marshmallows. Confectioners in early 19th century France pioneered the innovation of whipping up the marshmallow sap and sweetening it, to make a confection similar to modern marshmallow. The confection was made locally, however, by the owners of small sweet shops. They would extract the sap from the mallow plant's root, and whip it themselves. The candy was very popular, but its manufacture was labor-intensive. In the late 19th century, French manufacturers thought of using egg whites or gelatin, combined with modified cornstarch, to create the chewy base. This avoided the labor-intensive extraction process, but it did require industrial methods to combine the gelatin and cornstarch in the right way. Another milestone in the development of the marshmallow was the extrusion process by the Greek-American confectioner Alex Staumack in 1954. In this process, marshmallow mixture is pumped through extrusion heads with numerous ports aligned next to each other which form continuous ropes of marshmallow. This invention allowed marshmallows to be manufactured in a fully automated way, and gives us the familiar cylindrical shape of today's marshmallow. To make marshmallows in large quantities, industrial confectioners mix water, sugar, and corn syrup in massive kettles which are then heated to a precise temperature and cooked for a precise time. This mixture is then pumped to another kettle to cool. Rehydrated gelatin is added and blended in. Once the mixture has cooled enough to not denature the gelatin, to give the marshmallow its fluffiness, it is pumped through a blender while air is pumped into it. At this point, it still needs to be cooled further, so it will hold its shape when extruded. It is pumped through a heat exchanger prior to being pumped through the extrusion heads and onto a wide conveyor belt. The conveyor belt is coated in cornstarch and more cornstarch is dusted onto the top of the marshmallow extrusion as it passes down the conveyor. A large knife the width of the conveyor is located at the end of this conveyor table that chops the extrusion into the size marshmallow desired. The pieces will then be tumbled in cornstarch in a large drum, so the marshmallow to form its familiar skin and to allow pieces that did not get cut all the way to break apart. Marshmallows, like most candies, are sweetened with sucrose. They are prepared by the aeration of mixtures of sucrose and proteins to a final density of about 0.5 grams per milliliter. The molecular structure of marshmallows is simply a sugar solution blended with stabilizing structure agents such as gelatin, xanthan gum, or egg whites. The aforementioned structural components prevents the air from escaping and collapsing the marshmallows during aeration. Function of ingredients. Today, the marshmallow consists of 4 components. These include sugar, water, air, and a whipping agent, usually a protein. The type of sugar and whipping agent varies depending on desired characteristics. Each brand of marshmallow has its own specific formula for how to produce the perfect marshmallow. No matter how they are made, each ingredient plays a specific role in the final product. The marshmallow is a foam, consisting of an aqueous continuous phase and a gaseous, air, dispersed phase. In addition to being a foam, this also makes marshmallows an aerated confection because it is made up of 50% air. The goal of an aerated confection like marshmallow is to incorporate gas into a sugar mixture and stabilize the aerated product before the gas can escape. When the gas is introduced into the system, tiny air bubbles are created. This is what contributes to the unique textural properties and mouthfeel of this product. Protein. Proteins are the main surface active agents responsible for the formation and stabilization of the dispersed gas phase. Surface active molecules are prominent at the surface of a liquid, rather than at the bulk of it due to their structure. A portion of the molecule is hydrophilic with a polar charge, and another portion is hydrophobic because it is nonpolar. The nonpolar section has little or no affinity for water, and so it is energetically favorable for this section to be as far away from the water as possible. However, the polar section is attracted to the water and has little or no affinity for the air. Therefore, the molecule orients at the surface with the polar section in the water. with a nonpolar section in the air. Two primary proteins that are commonly used as aerators in marshmallows: albumin, egg whites, and gelatin. Albumin, egg whites, albumin is a mixture of proteins found in egg whites, and is utilized for its capacity to create foams. In a commercialized setting, dried albumin is used as opposed to fresh egg whites. In addition to convenience, the advantages of using dried albumin are an increase in food safety and the reduction of water content in the marshmallow. Fresh egg whites carry a higher risk of salmonella and are approximately 90% water. This is undesirable for the shelf life and firmness of the product. For artisan-type marshmallows, prepared by a candy maker, fresh egg whites are usually used. Albumin is usually never used on its own when incorporated into marshmallows, and is used in conjunction with gelatin. Gelatin is the aerator most often used in the production of marshmallows. It is made up of collagen, a structural protein derived from animal skin, connective tissue, and bones. Not only can it stabilize foams, like albumin, but when combined with water it forms a thermally reversible gel. This means that gelatin can melt, then reset due to its sensitivity to temperature. The melting point of gelatin is 95 to 100 degrees Fahrenheit. Body temperature. This is what contributes to the melt-in-your-mouth sensation when a marshmallow is consumed. When the marshmallow hits your tongue, it immediately starts to melt due to the body temperature going from a solid to a liquid. Temperature needs to be just above the melting point of the gelatin, so as soon as it is formed, it cools quickly and the gelatin sets, retaining the shape. If the marshmallow rope mixture exiting the extruder during processing is too warm, the marshmallow starts to flow before the gelatin sets. Instead of a round marshmallow, it will take a more oval form. Therefore, when marshmallows are being produced at home or by candy makers, the gelatin is added after the syrup has been heated and cooled down. This way the gelatin can avoid heat degradation. In commercial operations, the gelatin is simply cooked with the sugar syrup, rather than being added later after the syrup has cooled. In this case, kinetics play an important role, with both time and temperature factoring in. If the gelatin was added at the beginning of a batch that was then cooked to 235 to 240 degrees Fahrenheit in 20 to 30 minutes, a significant amount of gelatin would break down. The marshmallow would have reduced springiness from that loss of gelatin. But since the time the syrup spends at elevated temperature in modern cookers is so short, there is little to no degradation of the gelatin. In terms of texture and mouthfeel, gelatin makes marshmallows chewy by forming a tangled 3D network of polymer chains. Once gelatin is dissolved in warm water, dubbed the blooming stage, it forms a dispersion, which results in a cross-linking of its helix-shaped chains. The linkages in the gelatin protein network trap air in the marshmallow mixture and immobilize the water molecules in the network. The result is the well-known spongy structure of marshmallows. This is why the omission of gelatin from a marshmallow recipe will result in marshmallow creme, since there is no gelatin network to trap the water and air bubbles. Sugars. Marshmallows are an amorphous solid because of how the sugars crystallize. This is because the crystals formed are not grained and very fine in size, as opposed to its crystalline counterpart where the crystals are grainy and larger in size. This is why temperature plays such an important role in the production of marshmallows. To make an amorphous solid like marshmallow, the sugar syrup solution, sucrose, corn syrup, and invert sugar, is heated at a high temperature. It is then cooled so rapidly that no crystals have time to form. The quick cooling of the liquid in open air does not allow the sucrose molecules to form crystals. So glass, amorphous crystals are created instead. In most confections, a combination of different sugars is used, each of which influence the solubility concentration of one another. The presence of invert sugar and/or corn syrup causes a substantial decrease in sucrose solubility. Due to the competition among the sugar molecules for water, a traditional marshmallow might contain about 60% corn syrup, 30% sugar, and 1% to 2% gelatin. The corn syrup-sugar ratio will provide only about 35% to 40% solids to prevent crystallization. Crystallization can be further avoided with proper selection of the corn syrup type. A higher conversion corn syrup will contribute more invert sugar to the formula, which inhibits crystallization. If a grainy textured marshmallow is desired, you simply increase the sugar ratio to the point where it will crystallize about 60% to 65%. Then whip it, and add a little powdered sugar. As it cools, the sugar crystallizes out to form the grained marshmallow. Sucrose. Sucrose is another ingredient utilized in most aerated confections. It is a disaccharide that consists of one glucose and fructose molecule. This sugar provides sweetness and bulk to the marshmallow, while simultaneously setting the foam to a firm consistency as it cools. Sucrose, and sugars in general, impair the ability of a foam to form, but improve foam stability. Therefore, sucrose is used in conjunction with a protein like gelatin. The protein can adsorb, unfold, and form a stable network, while the sugar can increase the viscosity. Liquid drainage of the continuous phase must be minimized as well. Thick liquids drain more slowly than thin ones, and so increasing the viscosity of the continuous phase will reduce drainage. A high viscosity is essential if a stable foam is to be produced. Therefore, sucrose is a main component of marshmallow, but sucrose is seldom used on its own, because of its tendency to crystallize. The crystallization process is explained by Le Chatelier's principle. It states that a system shifted away from equilibrium acts to restore balance by reacting in opposition to the shift. So, an increase in temperature causes the system to decrease in energy to bring the temperature down. The energy is then absorbed as the chemical bonds from the sucrose break down. This cools the system down, so more sucrose molecules break apart and dissolve in the solution. When the solution cools down, we see sugar crystals form. This is also explained by Le Chatelier's principle that says a decrease in temperature causes a system to generate energy to bring the temperature up. Since the formation of chemical bonds always releases energy, more sucrose molecules will join crystals already forming to increase the temperature. This explains why crystallization occurs when the temperature decreases. In marshmallow processing, these are the steps that occur as the sugar syrup solution is being heated and cooled. Corn syrup. Corn syrup, sometimes known as glucose syrup, is a syrup containing dextrin, maltose, and dextrose. Partial hydrolysis of cornstarch obtains it. Corn syrup is important in the production of marshmallow because it prevents the crystallization of other sugars, like sucrose. It may also contribute body, reduce sweetness, and alter flavor release, depending on the dextrose equivalent, DA, of the glucose syrup used. The DA is a measure of the amount of reducing sugars present in a sugar product in relation to glucose. Lower DA glucose syrups will provide a chewier texture, while higher DA syrups will make the product more tender. In addition, depending on the type of DA used, can alter the sweetness, hygroscopicity, and browning of the marshmallow. Corn syrup is flavorless and cheap to produce, which is why candy companies love using this product. Invert sugar equals. Invert sugar is produced when sucrose breaks down due to the addition of water, also known as hydrolysis. This molecule exhibits all the characteristics of honey except the flavor because it is the primary sugar found in honey. This means that invert sugar has the ability to prevent crystallization and produce a tender marshmallow. It is also an effective humectant, which allows it to trap water and prevent the marshmallow from drying out. For some candies, this is not a good trait to have, but for marshmallows, it is an advantage since it has a high moisture content. Additional ingredients flavors unless a variation of the standard marshmallow is being made. Vanilla is always used as the flavoring. The vanilla can either be added in extract form, or by infusing the vanilla beans in the sugar syrup during cooking. This is the best technique to get an even distribution of flavor throughout the marshmallow. Acids, such as cream of tartar or lemon juice, may also be used to increase foam stability. Addition of acid decreases the pH. This reduces the charge on the protein molecules and brings them closer to their isoelectric point. This results in a stronger, more stable interfacial film. When added to egg whites, acid prevents excessive aggregation at the interface. However, acid delays foam formation. It may therefore be added toward the end of the whipping process after a stable foam has been created. Manufacturing process. Commercial process. In commercial marshmallow manufacture, the entire process is streamlined and fully automated. To begin, the gelatin is simply cooked with the sugar and syrup. After the gelatin-containing syrup is cooked, it is allowed to cool a bit before air is incorporated into the system. Whipping is generally accomplished in a rotor-stator-type device. Compressed air is injected into the warm syrup, held at a temperature just above the melting point of gelatin. In a marshmallow aerator, pins on a rotating cylinder rotor intermesh with stationary pins on the wall stator to provide the shear forces necessary to break the large injected air bubbles into numerous tiny bubbles that provide the smooth, fine-grained texture of marshmallow. A continuous stream of light and fluffy marshmallow exits the aerator on its way to the forming step. The marshmallow candy is typically formed in one of three ways. First, it can be extruded in the desired shape and cut into pieces, as done for jet-puffed marshmallows. Second, it can be deposited onto a belt, as done for Peeps. Finally, it can be deposited into a starch-based mold in a mogul to make various shapes. Homemaking process. The process for making marshmallow at home differs from manufacturing plant processes. At home, a mixture of corn syrup and sugar is boiled to about 227 degrees Fahrenheit, 108 degrees Celsius, to give a moisture content of 20% or so. In a separate step, gelatin is hydrated with enough warm water to make a thick solution. Once the sugar syrup has cooled to about 100 degrees Fahrenheit, 38 degrees Celsius, the gelatin solution is blended in along with any desired flavoring, and whipped in a KitchenAid or Hobart-type mixer to reach the final density. The marshmallow is then scooped out of the bowl, slabbed on a table, and cut into pieces for serving. Toasted marshmallows, a popular camping or backyard tradition in the United Kingdom, North America, New Zealand and Australia, is the roasting or toasting of marshmallows over a campfire or other open flame. A marshmallow is placed on the end of a stick or skewer and held carefully over the fire. This creates a caramelized outer skin with a liquid, molten layer underneath. Major flavors, compounds and color polymers associated with sugar browning are created during the Caramelization process. S'mores are a traditional campfire treat in the United States, made by placing a toasted marshmallow on a slab of chocolate which is placed between 2 graham crackers. These can then be squeezed together to cause the chocolate to start to melt. Dietary preferences. The traditional marshmallow recipe uses powdered marshmallow root, but most commercially manufactured marshmallows instead use gelatin in their manufacture. Vegans and some vegetarians avoid gelatin, but there are versions which use a substitute non-animal gelling agents such as agar. In addition, marshmallows are generally not considered to be kosher or halal unless either their gelatin is derived from kosher or halal animals or they are vegan. Marshmallow creme and other less firm marshmallow products generally contain little or no gelatin, which mainly serves to allow the familiar marshmallow confection to retain its shape. They generally use egg whites instead. Non-gelatin, egg-containing versions of this product may be consumed by ovo-vegetarians. Several brands of vegetarian and vegan marshmallows and marshmallow fluff exist. See also, The Marshmallow Explained at HowStuffWorks.com.